The truth is that it is not possible for you to do calculations in physics, in any topic in physics, if you don't know the basic equations that are in that particular topic. And that's why it's not possible for us to carry out any calculation in elasticity of materials if we don't know the basic equations from Hooke's law. Welcome to Physics Meal. In this video, I'm going to show you the basic equations that we will need in order to carry out calculation, whether it's for UTME or WASI in Hooke's law. All right, let's begin. Now, from the previous video, you remember that we established from Hooke's law, that F, that's force, is equal to what? Equals to KE. So recall that F is equal to what? KE. Okay. Now, we made an important statement. We say that K is constant for any given what? Material. So if I'm talking about iron, the K for iron will remain the same. So if this is iron and this is another iron, then the force constant of this iron is the same as the force constant of this particular one, iron. Iron will have the same force constant. So K is constant for any given material. Now let's assume that we have an initial force F, right? We have an initial force F1. Let's say we have an initial force F1. If you apply this initial force F1 on an elastic material, you are going to produce an extension E1. Do you get that? Okay, let's look at it practically so that we can actually put it down. Now, in any elastic material, as we can see here, this is a spring. It's an elastic material. Now, no force has been applied here, right? We don't have any force applied, right? No force applied. So the natural length, the original length, the unstretched length of this material, it has an original length. It has an unstretched length, right? Original length, unstretched length. Don't mind me. The unstretched length or the natural length, the length when there is no application of force, that's the original length, right? The unstretched length, the natural length. Now we have the natural length. So let the natural length or the unstretched length, let L naught be equal to the natural length, natural or unstretched or original length of an elastic material. Now, if you apply a force, a new force now, that's a force on this particular body now, on this particular spring. If you apply a force, remember here, no force has been applied for this natural length, just as it is in this place now. No force has been applied. So this is the natural length of the spring. Now, if I bring a force, if I apply a force now on this spring, let me apply a force. Let's say I apply the force. This force will produce a new length, right? So this force will cause an extension. So this extension will make this to have a new length. So if a force F1 is applied on the elastic material, a new length L1 will be produced. A new length L1 will be produced. So the length will now move from the original length, the original or the natural length or the unstretched length. It will now move from the natural length to a new length L1, and that's what we saw here. If I remove this is the natural length, if I fix this back, you now see, if I remove this, that's the natural length. The moment I will add, if I add this now, it will now extend to a new what? A new length L1 by the application of this force F1, right? This force is in form of mass, and I'm using mass as the force, that's the load now, okay? Now, it will produce a new length L1. Supposing I decide to add another force, I hope you know that the length will also increase. So if I add another force, let's say I add another force now, a new length has been produced as a result of addition of another force. So similarly, okay, let's use here. Similarly, if a new force or another force, if another force F2 is applied on the elastic material, it will produce another new length L2. So if I apply a force F1, it will produce what? It will produce a length of what? L1. So a force of F1 will move the length of the spring from what? Its natural length to a new length. Just like if I have this is the natural length on stretch length, no force has been applied on this. But if I do this now, it has increased in size. A new length has been produced now. If I continue, another length. So in the first case, I applied a force, a new length. So their first force I applied produced this new length. If I apply another force, the second force now will produce another new what? Another new length. So that's what we mean by this statement, that F1, a force, will produce a new length L1. Now F2, a force of F2 will produce another new length what? F2. Now, sorry, L2. Now, what will be the extension? For F1 now, the extension produced. So for F1, the extension E1 will be E1 equals L1 minus L0, right? Yeah, that's what it will be. If I have a spring like this, and this is the original length of that spring when I did not add any load. So this is L0, the original length. If you add a load now, if I add a load on this is the original length now. If I add a load to this length will extend as a result of the application of the load. Is L0, then this length will extend. From here to here is the new length L1 when I add a load F1. So the new length now is L1. It moved from this original length, there will be additional length due to the application of this force. So this is the extension. This extended from here to this place, so it is E1. How will I get E1? If I use L1 to minus L0, what I will have is what? E1, right? Yes, that's what will happen. So from here to here is L what? Not. From here to here is L1. What will be the extension? This minus this. If you remove from here, if you remove L0 from what? L1, now you have the extension. You have the extension. Okay. Now the same thing will happen. It means also that for F2, the extension E2 will be E2 equals what? L2 minus L0. Let me call this equation 2 and let me call this equation 3. This is our equation 1. Now we don't have problem again because we can now start generating our equations. Now what did we say about Hooke's law? That F is equal to what? F is equal to KE. F is KE. Very beautiful. F is KE. F is KE. Don't forget that. F is KE. Let's drop this. F is KE. F is KE. So, if F is KE, it means that since F is equal to KE, it means that F1 will be equal to K1 E1, right? And what? And F2 is equal to K2 E2, right? So, but K is constant for any given material. Thus, K1 will be equal to what? K2. K1 will be equal to K2. Now, you also remember that we have established that if F is equal to KE, it means that K is equal to F over E, right? K is F over E. So, let's say recall that K is F all upon E. K is equal to F over E. So if F is KE, K is F over E. That's from equation 1. Okay? It means then K1 will be equal to what? F1 over E1. And what? K2 will be equal to what? F2 over E what? E2. So K1 will be equal to this and K2 will be equal to this. But we know that K is constant. K1 is equal to K2. That means the whole of this is equal to the whole of this. Thus, we can write comfortably. We can write comfortably that F1 over E1 is equal to F2 over E2. So I can call this equation 4. Right? So the first apply force, the second apply force. The first extension, the second what? Extension. So this is the extension due to force F1. This is the extension due to force F2. Now recall that from equation 2 and 3, from equations 2 and 3, we have that E1 is equal to L1 minus L0 and E2 is L2 minus L0. So if I substitute the values of E1 and E2 from this place into this equation 4, that means E1, instead of writing E1 here, I can write L1 minus L0 because the whole of this is E1. If I substitute, I will now have this. So equation 4 can be written as F1 over what? L1 minus L0 is equal to F2 over L2 minus L0. Let me call it equation 5. Now this equation 5 can be modified in so many ways. You know, I can still write this as F1 over E1 equals F2 over what? L2 minus L0. In a situation when E1 was given to me in equation, but I don't know E2, but I know L2, and maybe I'm looking for L0, I can just, the only one I may substitute in terms of length may be this, right? So it's possible that I can keep my E in one part and substitute L for L, the L0 for it. For example, here, I kept this, but I know that E2 is equal to this, so I use this to replace it. Similarly, I can still write it in this way, still mean the same thing, and have E2, depending on the nature of the word of the equation. So we have 5 equations that we are going to use to carry out calculations, and it is important that you take note of these 5 equations and their modifications Very important. Now, another important thing before I go, another important thing that you must note is that force is in Newton, right? That's the unit of force. force is in Newton. Force constant is in Newton per meter. If you look at the unit of force constant, so I clean my equation 5 L1 minus L0 equals F2 over L2 minus L0. Now, if you look at force constant, K is equal to F over E. Force is measured in Newton and extension in meters, so Newton per meter, that's the force constant. Now, let us note that force can also be given in terms of mass. Then in the equation, instead of giving you force, they can give you mass. So when you are giving masses, convert it to weight. That's to weight, using the fact that F is equal to what? Mg. That's the force as a result of weight is mg. So when you are giving masses, convert the mass to what? To weight, as you solve the what? The problem. Correct. You can just make a little note on one part of your book of these 5 what? These 5 equations, because we are going to start using them in our next video. We'll use them to solve a lot of problems in our next video. Thank you for watching our video. In our next video is going to be calculation. Make sure that you subscribe to our YouTube channel. Make sure you follow us on Facebook at Mathematics and Science Mail, or look for Engineer Ike Okechukwu on Facebook and follow him. And then subscribe to our YouTube channel at Mathematics Mail 1 so that you will enjoy all our meals. Thank you and God bless you.